Okay, good afternoon. Today is March 25, 2024, and it's a pleasure for me to introduce a talk of Samuel Lopes, a colleague from my University of Porto, and he's going to talk on torsion-free representations of Smith algebras. Please.
Okay, so thank you very much. And first of all, thank you very much to the organizers of this great seminar for the opportunity to speak here. So, and sorry, I hope I didn't disappoint anyone. I had a last minute change of topic from what I had planned. So I decided to switch to this a different topic. My previous topic was cohomology. Because I thought this was kind of maybe a lighter talk, and some people had seen my previous talk, the previously planned talk, so I switched gears. And so I'm going to talk really, I mean, the context is motivated by geometry and non-commutative algebra, and I'll try to explain. I'll actually spend most of my talk explaining this this connection. And before I forget, I should mention that this, I mean, the relevant part of the talk, so the new results, which will appear at the end, are joint work with Slava Futorny and Eduardo Mendonça. Okay, and I should also mention that so these results and this work are going to appear in an issue of the Journal of Algebra dedicated to Georgia Bankart, and so I would like to make this dedication here, dedicated to her memory. And it's in fact related, I mean, to her work, I believe, in several ways. First of all, it touches on her own work. And second of all, we believe, I think I'm speaking for my co-authors as well, we believe that it's the kind of thing that she would have appreciated if she were here with us. So let me start. And as I said, the big motivation for I'm going to tell you comes from geometry and the interplay between algebra and geometry. And so this maybe starts in a certain sense with Felix Klein and with this idea of equating groups and geometries, in the sense that, I mean, any geometry will have its relevant group of permissible transformations. For example, if you're looking at Euclidean geometry, this group would be the Euclidean group, which is the group of isometries. So the linear ones form the orthogonal group, and then you have the translations. From the geometric, sorry, this is from the geometric point of view, and these would be the relevant transformations. From the group theory point of view, so if you have this group acting on this space, then the orbits will form the geometric object. So imagine in Euclidean geometry, you take a triangle and then act on this triangle by every possible isometry. You will just get all of the triangles which are equal to your initial triangle. So that is the geometric object. So it's kind of the quotient space. You have some kind of a space where your geometry is taking place, and the quotient space by the action of this group is really what your geometric objects are. So this is kind of the dictionary, or the way to think about both things at the same time. And the other connection, which is kind of a continuation of this, is the kind of the inspiring work of Emmy Noether, and I'm not mentioning David Hilbert, but I should, of Emmy Noether, where, you know, this connection between invariance and symmetry is made very explicit and relevant from the physical point of view, for example. And while mentioning Hilbert, this would be looking at invariant rings under the actions of these groups, because this should correspond to the coordinate rings of these quotient spaces of a geometric space acted on by a group of transformations. Okay, so this is kind of the idea, and I might as well mention that I will often confuse the geometry with the algebra, in the sense that I will confuse the geometric variety, for example, with its coordinate ring. Namely, for example, I will when I say the plane, I'm probably going to mean the polynomial ring in two variables, which is the coordinate ring of the affine two space, and things like this. So this is the kind of setup that I want to be in. So, I mean, when one thinks about these groups and about geometry, I think, at least for me, one of the first things that I think about is the Platonic solids, because they're just nice geometric objects, very symmetric, very regular, and they have nice symmetry groups. They're finite groups, of course, but they're interesting. For example, you can get the alternating group A5, so as one of these symmetry groups. So this is kind of the first thing that I think about, and then the next thing I think about is, well, I mean, all of these Platonic solids, for example, live inside a sphere. They can be inscribed in a sphere. And so their symmetry groups are subgroups, which are finite subgroups of the symmetry group of the sphere. So here's the sphere, the master of all of these Platonic solids. And its symmetry group is really the rotation group, which is the group SO3. Okay, well, we could consider also reflections, and we would have O3, the 3x3 orthogonal group, but that's not much of a difference. It's essentially the same thing. You need a product with Z2. So this is the symmetry group of the sphere. You can go a little bit further if you want. If you want kind of a simply connected group, you could consider SU2, or if you're more physically inspired. And I'm saying this for a reason, which will come up soon. So essentially, I mean, the kind of symmetry group that we're talking about is SO3 or SU2 or SL2. And so the question is, you know, coming from all of this is, I mean, the first natural question is, what are the finite subgroups of the spherical group? What are the finite subgroups of SO3 or the finite subgroups of SU2? Okay, so these could be nice groups that could have nice actions. Okay, so here's what the finite subgroups of SO3 are. So they come in several flavors. They're the cyclic groups, they're the dihedral groups, and then there's the symmetry groups of the 5 Platonic solids. Okay, the group A4, the group A5, and the symmetric group S4. Okay, and they all, in terms of these Platonic solids, they all reveal something about these Platonic solids. For example, I mean, this, at least to me, is quite inspiring. If you look at S4 as a symmetry group of the cube, and you think, okay, so this is permutation of 4 things. What are the 4 things that are being permuted here kind of freely? Okay, it's not the vertices, there are too many vertices, so what could it be? And it turns out that it's one way to think about it is the space diagonals in this cube. So it's clear that any isometry of the cube will permute to space diagonals. What is less obvious at first sight is that you can realize any permutation of these 4 space diagonals by an isometry. Okay, so, you know, looking at these symmetry groups will tell you things that maybe are not so visible in your initial object. This is more so even in the dodecahedron, when you have to think about what are the 5 things that are being permuted, but I will not get into that. But so the point is, here's the classification of the finite subgroups of the rotation group. And you'll notice that, you know, I said they come in flavors, and these flavors are given by letters. And you might recognize these letters, okay? You might want to complete the alphabet that's displayed here. There's an A, B, C, D, E, F, G. And if you do, of course, what you get is the Dinkin diagrams. Okay, so I've shown you before the simply laced cases, and then if you add the non-simply laced cases, you get all of the Dinkin diagrams. Okay, and this is paradigmatic because I mean these Dinkin diagrams are are this great combinatorial tool that classifies almost everything. Okay, so well, this is a non-associative seminar, so everyone knows here that they classify the simple Lie algebras over an algebraically closed field of characteristic 0. The simply laced ones I've shown you also classify the finite subgroups of SO3. Okay, and there's a combinatorial way to see that, to do this construction, and it's related to something called the Mackay correspondence, which I will come to, which is a very nice correspondence, which I'll come to soon. They also classify, for example, the finite dimensional algebras, which have finite representation type. Okay, these also, I mean, usually they come just in the simply laced ones, but there's an interpretation of the other ones in terms of something called species, although not the combinatorial species, but different kind of object, which interprets the non-simply laced diagrams also in the setting of representations of finite dimensional algebras. Okay, but they do classify many other things, and one of these things, which is going to be my main object of interest, is certain singularities of geometric objects. Okay, and this is what I'm going to explain in a second. So these singularities come by two names, depending on your preference. They're called Kleinian singularities, but they also are called Duval singularities for the more francophone people. And I'm just going to show you for now a table, and then I'll show you how this table is constructed. So related to the class AN, which had to do with a cyclic group, you have a certain graph, which is the AN kind of graph, and you have a certain equation, which is the equation that you're seeing, x squared plus y squared plus z to the n plus 1, okay, equals 0. Okay, sorry, minus, x squared plus y squared is equal to z to the n plus 1. Okay, there are typos here in these equations. Okay, so what is this correspondence between these types and these equations that have, on one hand, they're related to these groups, on the other hand, they're related to these geometric objects? How is the connection made? And I will explain to you, and this is exactly via invariant rings. Okay, so here's how it goes, for example, for the cyclic group of order 2. Okay, so take the cyclic group of order 2, it acts on the plane. Here, I mean the affine 2 space by sending u to minus u and v to minus v. And so this induces an action on the coordinate ring, on the polynomial ring in these two variables, u and v, and the action is the same, okay? And you might ask, well, then what are the invariants in this ring? Well, it's clear just by looking there that u squared is invariant under this action, and that v squared is invariant under this action, and that u times v is invariant under this action. Okay, but it turns out that all of the invariants are obtained from these three invariants. So they're generated by these three elements, u squared, v squared, and u times v, although they're clearly not algebraically independent because, well, the product of u squared and v squared is the square of the third element. So there's a dependence relation. And so you can identify this invariant ring with a quotient of the polynomial ring in three variables. Here, think of x as u squared and z as v squared, and then y as u times v. Okay, and so you get this relation here, x times z is equal to y squared. So this is what the invariant ring looks like. So what is this surface, y times z is equal to y squared? If you make a change of variables, if you replace x with a minus b and z with a plus b, then you get the equation for the cone. You get a squared minus b squared is equal to y squared. And so you get a squared is equal to y squared plus b squared. So it's the equation that you find here in the table, the first yellow square, that's a1. That's the equation that you get, and that's this double cone, which has a singularity at the origin. Okay, so that's what a Kleinian or a Duval singularity is. Okay, so it's a singularity of this type, and they're classified by the Dynkin diagrams. And you can see this classification in the way that I mean, if you're more algebraically, there's a direct way of seeing this, but the way that I prefer, because I'm a little bit more algebraically inclined, is I look at the group, I look at the natural action of the group on on affine space. I look at the invariant ring, and then I see what's the surface that's coming up in this invariant ring, and this will be the Kleinian singularity. So these surfaces will always have these singularities, but they're not very, I mean, they're special kinds of singularities which make them kind of nice. Okay, so this is a way of seeing this correspondence between the Dynkin diagrams, or these finite subgroups of SO3, with these nice surfaces appearing here, which have these special kinds of singularities. Okay. Now this correspondence goes a little bit further. Okay. And it goes further in the following way. So as I said, this is related to something called the Mackay correspondence, which has many facets. So one facet is a way of classifying the finite subgroups of SO3, and you can do that via a graph, which is constructed via this Mackay correspondence, or you can use the Mackay correspondence to classify these Kleinian singularities. Okay, but besides that, this correspondence gives you also a correspondence, a bijection, between the irreducible representations of your finite group and a basis for the cohomology space, not of your singularity, that y is not a singularity, the y is a resolution of your singularity. Okay, so these singularities, as said, are kind of special, and they have something called the Crepant resolution. It's a concept defined by Miles Reed. And this y is the Crepant resolution, which will always exist for Kleinian singularities. And so this Mackay correspondence gives a bijection between the irreducible representations of the group and a basis in cohomology, and at the same time, a bijection between the conjugacy classes in the group and a basis for the homology. Okay, so I mean, if you remember that there are as many irreducible representations as conjugacy classes, then you'll see that there's this nice correspondence between cohomology and homology, which you can interpret as the Poincare duality. Okay, the duality between kind of geometric forms, which are given by homology, and kind of differential forms, if you will, which are given by cohomology. Okay, so it's a really nice picture, and essentially, this is really what I want to tell you about this, about these Kleinian singularities. So where do I want to go next? Well, I want to take a point of view of making everything non-commutative. Okay, so of course it's difficult to imagine non-commutative geometry, but we can, as we do in many areas of mathematics, and that's always a breakthrough, as long as I have a dictionary and as long as I can generalize on one side, then I can kind of generalize on the other side. Okay, so I can think of non-commutative geometry as as some imaginary object that I have, which corresponds to a non-commutative coordinate ring. Okay, so this is the point. So these invariant rings that I've been talking about are commutative, but now I want to make them non-commutative. And the action of these finite groups is taking place in a affine space, in a affine 2 space, so in the polynomial ring in 2 variables, and I want to deform this and make this non-commutative. Okay, so specifically, this is what I'm going to do, and I'm going to do this kind of in a strange way. I'm going to introduce the an object which is part of every talk that I give. I don't think that I've given any talk without mentioning the first file algebra, and so this will not be an exception. So I'll introduce the first file algebra in kind of a strange way, but there's a reason for that. I mean, so if you have a poset, a finite poset, under certain conditions, namely, well, the ones that I have on the slide, which I don't want to repeat, you can define two operators on the linearization of that poset. So the same way that you linearize a group and form the group algebra, you can linearize the poset and look at formal linear combinations of elements of your poset. And the two operators are the following. So D will work downwards, which means that it will send an element Y in your poset to the sum of all of the elements which are strictly below it in the poset. Okay, and by strictly, I mean immediately, not everything all the way down, just the ones that are just one step down in the Hasse diagram. And the U operator is the one that takes an element in your poset, an element Y, and associates with it the sum of all of the elements which are immediately above it. Okay, so let me give you an example. Here, the Young's lattice of partitions. Okay, so what would this do? Let's take this central part. I don't know if people can see my cursor or not. I'm circling around. Okay, good. So I'm circling around this partition 2, 1. So the U operator, well, yeah, the U operator will assign to this element the sum of these three. Okay. And now when I apply the down operator to these three, then I'll get these three, but with multiplicity. So this one will appear with multiplicity 1 coming from this one. This one here will appear with multiplicity 3 because one copy is coming from here, another one's coming from here, and another one's coming from here. And this one will appear with multiplicity 1. So what I've done is I started here, I applied the up operator, and then I applied the down operator. Now let me do the same thing in the opposite order. So first I apply the down operator, so I get the sum of these two. And now I apply the up operator. I will get just this one with, I will get this one with multiplicity 1, this one with multiplicity 2 coming from these two, and this one with multiplicity 1. So when I look at the difference, these will, the two extreme ones will cancel, and this one, I was looking at something with multiplicity 3 minus multiplicity 2, so I will get back the original element in the poset, the original partition. So long story short, by example, and this is true in general, these two operators satisfy this nice relation, which is du minus ud is equal to the identity, okay? And this is a very nice relation. It's the defining relation for the file algebra, the first file algebra. Okay, I'll give you the more standard way of introducing the first file algebra. But the reason why I'm doing this, well, first of all, maybe, I mean, if you haven't seen this before, you'll find this amusing. And the other reason is that this is one of the things that that motivated Georgia Bankart and Tom Roby to introduce this class of algebras called down-up algebras. Okay, so they were looking. So I think, as far as I know, Tom Roby was visiting Georgia, and they were looking at these operators on posets, which had been, studied by Stanley and Fomin, and they were trying to, look at other posets which satisfied other kinds of relations. And motivated by that, so that's the combinatorial inspiration, and simultaneously motivated by the Serre relations. So if you've seen some things on simple Lie algebras or semi-simple Lie algebras, you might have seen the Serre relations, which give you the relations that the maximal nilpotent subalgebra of a simple Lie algebra satisfy. So these are called the Serre relations. And if you look at this, I mean, it's a little bit distressing, maybe, maybe a little bit I mean, scary relations. But if you set gamma equal to 0, they do look like Serre relations or deformations of these Serre relations. Okay, so with the motivation coming from combinatorics and these differential posetsets, and at the same time coming from the representation theory of simple Lie algebras, they came up with this definition of the algebra generated, if you want, by two operators D and U, which satisfy these relations, where alpha, beta, and gamma are certain parameters in your field. Okay, and they call these down-up algebras. Okay, so examples of down-up algebras are the enveloping algebra of SL2. Okay, so here you have SL2. It's as a Lie algebra, it's three-dimensional. It has a basis given by H, E, and F, and the commutation relations are the ones that I'm underlining here. So H acts semi-simply on this Lie algebra, sending E to 2 times E, and F to minus 2 times F. And it's seen as the commutator, it's created as the commutator of E and F, okay? And this enveloping algebra of SL2 is then the down-up algebra with parameters 2, minus 1, minus 2, okay? So at least this class includes the enveloping algebra of SL2. It also includes the enveloping algebra of the Heisenberg Lie algebra. So that's a three-dimensional Lie algebra, nilpotent Lie algebra, as opposed to SL2, which most times, at least in characteristic 0, will always be simple. For the Heisenberg Lie algebra, you have two elements whose commutator is Z, and Z is central. Okay, so this is called the Heisenberg Lie algebra, and its enveloping algebra is again a down-up algebra. Okay, there's a deformation of this Heisenberg Lie algebra called the quantum Heisenberg algebra, and I mean, depending on what you want, I mean, you can just look at these three relations and they're kind of deformations of the previous ones. If you think of the Lie bracket as a commutator, so here, instead of having Z as the commutator of X and Y, you have Z as a Q commutator of X and Y. Q is a scalar, non-zero scalar. Otherwise, you can look at it also as the quantized enveloping algebra of the positive part of SL3. That's another way of looking at it, okay? And this again is down-up algebra, and the connection is you just replace the 2 with quantum 2, which is 1 plus Q, okay? So these down-up algebras, you know, include a lot of nice algebras coming from Lie theory. What might not be clear is, why am I talking about this? I mean, there's a reason, and we will come back to Kleinian singularities. Okay, so just bear with me. So still related to these down-up algebras, I mean, 10 years, well, it's not 10 years ago, it's less, but recently, actually, with my former PhD student, Farrokh Khazavinia, we defined a class of algebras, which we called quantum generalized Heisenberg algebras. And so they're also given by three generators, X, Y, and H, okay? And the defining relations are the ones that I'm showing you here. So essentially, you think of how does one generator get past the other one? Okay, so the first relation tells you that if you have an H on the left and you want to move it to the right of an X, then you can, if you replace H with a certain polynomial in H, a fixed polynomial in H. For example, if you want H to commute with X, then your polynomial f of H would just be equal to H. Okay, if you want to have kind of a Weil algebra kind of relation, then your f of H would be, sorry, not a Weil algebra, a Lie algebra relation, you would have f of H equal to H plus 1, because this would tell you that the commutator of H and X is equal to X. So you'd get kind of the two-dimensional non-abelian Lie algebra there. So the same thing with Y, except that it works the other way around. Okay, so the idea is that X wants to be on the left, Y wants to be on the right, and H wants to be on the middle. And then how is H created? So if you're thinking about the SL2, H should be the commutator of X and Y. Okay, well, what we've introduced is that when you do a commutator of X and Y, you will get a certain polynomial in H, not necessarily H. Okay, and it doesn't even need to be an honest commutator. It might be a quantum commutator, a Q commutator. Okay, so these are the quantum generalized Heisenberg algebras, and I will explain why we introduced them and what's the relation with down-up algebras, and finally, what's the relation with these Kleinian singularities. Okay, so here goes. In around 2015, I had seen a paper by Lu and Zhao, where they introduced a class of algebras called generalized Heisenberg algebras. And this was motivated by some work in physics. So there had been literature in physics related to the logistic model, if I'm not mistaken. And so these groups of physicists were coming up with these algebras satisfying, certain relations, but it was kind of vague. Sometimes happens in physics literature. And so Lu and Zhao defined these algebras, which they call generalized Heisenberg algebras. And you'll see the relations here. And you see that they're essentially the relations that I showed you before, with one difference that, here the commutator of x and y in the algebras which we defined could be a quantum commutator. And in their case, so this commutator of x and y will be not an arbitrary polynomial, but a polynomial which is determined by f. Okay, whereas in our case, I'll show you these relations quickly. This polynomial g is completely independent from the polynomial f, and here you could have a quantum commutator. So what was the point of this generalization? Well, the point is the following. So we realized that these generalized Heisenberg algebras overlapped to a certain point with down-up algebras, but neither one of these two classes contained the other one. So there was an intersection, but neither class was bigger than the other one. And another, for me, disturbing thing was that the enveloping algebra of the Heisenbergly algebra is not, for this definition, a generalized Heisenberg algebra. And I did think that this was wrong. It should be. If the algebras are called generalized Heisenberg algebras, they should contain the Heisenberg algebra. And so this class that we defined here, this quantum generalized Heisenberg algebras, does include all of the down-up algebras. It includes all of the generalized Heisenberg algebras. It includes the normal Heisenberg algebra, its quantum version, and it includes many, many other algebras. Okay, so here's kind of I will show you a picture, a Venn diagram in a second, but now so I don't lose track with my slides. There's a particular kind of algebra which is going to be the connection with Kleinian singularities, and it appears in the title, which is called the Smith algebra. Okay, so the Smith algebra is this infinite dimensional algebra given by three generators. Okay, and it looks like this. So it's very similar to the enveloping algebra of SL2. The difference is that, well, you should have a 2 times y, a minus 2 times x, and here the polynomial g of h should just be h. That's the difference. Okay, the 2's don't make any difference except in characteristic 2. Otherwise, they don't make any difference. The g of h does make a difference. So if g of h is equal to h, then you do get the enveloping algebra of SL2. If g of h is not h, then you will not, in general, get the enveloping algebra of SL2, and you'll get other things. Okay. So these are called Smith algebras, and they are related to invariant rings of differential operators. They're related to vertex operator algebras. And this is the point, they're related to Kleinian singularities, to the point which I will explain briefly soon. Okay, so maybe I'll skip this, but I'll just remind you of the other more common definition of the Weil algebra, and that's in characteristic 0, it's the algebra generated by two operators on the polynomial ring. Okay, one is multiplication by t, the other one is derivative with respect to t. Okay, and for this, you'll notice it's very easy to check that these two operators satisfy this commutation relation. Delta times t minus t times delta is just the identity. Okay, And so it's an important algebra for many reasons. So what I've shown you before is that the Young's lattice, the linearization of Young's lattice, is a representation of the Weil algebra, of this first Weil algebra. It obviously appears in the theory of D modules. It appears a lot in geometry and in algebra. There are lots of open conjectures about even just the first Weil algebra. And it's seen as the algebra of differential operators with polynomial coefficients on the line, so on the affine line. Okay, and the Weil algebra can also be seen as a quotient. Now, it's a quotient of these quantum generalized Heisenberg algebras. This kind of a quotient. Okay. So the point here is that I said I wanted to make everything non-commutative. So I had a finite group acting on the polynomial ring in two variables. How am I going to make this non-commutative? I'm going to replace the polynomial ring in two variables by the Weil algebra. Okay. In a certain sense, they have the same kind of flavor because, I mean, although the Weil algebra is non-commutative, a basis for the Weil algebra will also be given by monomials in delta and t. You fix an order, for example, put the delta first and the t afterwards, and powers of delta times powers of t will give you a basis for the first Weil algebra. Okay, so you know, from this point of view, they look similar. Of course, then the Weil algebra is highly non-commutative, but it has very nice properties. In characteristic 0, it's a simple Noetherian domain. It has nice homological properties. So it will be a good candidate for a non-commutative version of the polynomial ring in two variables. So, okay. So just to show you the Venn diagram, the relation between these quantum generalized Heisenberg algebras and the down-up algebras and the generalized Heisenberg algebras, this is what this looks like. But I mean, what I'm interested now is in these actions of a finite group on the Weil algebra. Okay, so I will perhaps skip. I will show you briefly. Okay, so with my student, we did study the finite dimensional irreducible representations of these quantum generalized Heisenberg algebras. Okay, and given that they're somehow inspired or related to the enveloping algebra of SL2, it's not surprising that the classification also has some resemblance with the enveloping algebra of SL2. Okay, so I'll show you by way of example what the finite dimensional irreducible representations of these algebras look like. So they come in three flavors. Okay. So the usual flavor, which is the C type, the last one, is essentially like the representation theory of SL2 in characteristic 0. So the results that we have are in arbitrary characteristic, can be 0 or positive characteristic. This depends on, I mean, on the arithmetic of your field in principle. So you need to define two sequences, if you want, lambda and mu, two sequences of scalars, which need to satisfy certain conditions, which depend on the polynomial f, on the polynomial g, on the scalar q, and you know those equations might be sensitive to the field. Okay, and so it's these two sequences, lambda and mu, which characterize, which classify the irreducible representations. Okay, so in characteristic 0 for SL2, this is what they look like, and this is the type C in our classification. But then we also get diagrams which circle around. Okay, and I prefer to show you a very specific example, which will look kind of odd maybe. So pick for your polynomial f, this weird polynomial here of degree 2. Okay, it's picked so that, you know, some calculations become nice. Okay, and pick for your polynomial g1, which means that x and y will satisfy the Weil algebra relations. Okay, and q, for example, you can take q to be a primitive sixth root of unity. Okay, then the sequence is lambda and mu. So lambda is kind of classical. So it's the integers mod 3. And mu is quantum. So it's the quantum integers at a sixth root of unity. Okay, so you go from 0 up to 5, and then you get back to 0. Okay, so if you choose these parameters, then your representation will look like this. And I like this because this looks like two representations of SL2 put together in a way that it circles around. Okay, so the element H will be acting semi-simply with these classical numbers 0, 1, and 2. So they're repeated because we're working mod 3. And you have the X kind of constructing everything. So X will be circling around without killing anything. But you have the Y going in the other direction, and the Y does kill something because we're assuming that Q is a sixth root of unity. So the number 6, quantum 6, is equal to 0. Okay, so I think this is kind of a cute example of what the representations look like, and this is the general flavor of these representations. Okay, so we know what the irreducible representations of these quantum generalized Heisenberg algebras are in finite dimensions. Okay, so it's about time for me to explain to you what's the relation between this and the Kleinian singularities. Okay, so as I explained, now we're going to act not on the polynomial ring, but we're going to act on the Weyl algebra. So let's take the cyclic group of order n. So that's type A. So this is why we call them deformations of Kleinian singularities in type A. Okay, so the cyclic group can act on the Weyl algebra by scaling by an nth root of unity. So it sends t to omega times t and partial to omega inverse times partial, where omega is a primitive nth root of unity. So this defines an action of the cyclic group on the first Weyl algebra. And the question is, what are the invariants? What is the invariant ring? Okay, so again, the fixed ring, the ring of invariance, is again generated by t to the n. This is clear. I mean, it's clear that t to the n is invariant. Also, partial to the n is invariant, and the product of t times partial is also invariant. And it's again true that these three elements will generate all of the invariants, but there are two issues. They're not algebraically independent. This already occurred in the commutative case, but they do not commute. So this invariant ring is non-commutative. Okay, so what does it look like? So if you were commutative, you would be getting a Kleinian singularity, one of those nice pictures that I showed you. They don't commute, so the invariant ring is not a commutative ring. What is it? Well, it's precisely coming from the Smith algebra. Remember, the Smith algebra was that generalization of the enveloping algebra of SL2, where the commutator of y and x was this polynomial g. So it turns out that this invariant ring is a quotient of the Smith algebra, and a very nice quotient, because you'll remember that in SL2 you have a Casimir element, a central element which generates the center. The same is true for Smith algebras. There's a Casimir element, and the invariant ring is a quotient of the Smith algebra by a central element given by setting the Casimir equal to a certain scalar. Okay, and this is kind of interesting because, well, for the irreducible representations that I've shown you, well, for any irreducible representation which is finite dimensional, we know that the center will act as a scalar. So the irreducible representations for the finite dimensional irreducible representations will actually be representations of this invariant ring, because the Casimir will be acting by a scalar. I mean, you have to choose your scalar correctly. Okay, so you have to choose your representation correctly. Okay, so this is the starting point. So we look at this at this quotient of the Smith algebra as the deformation of a Kleinian singularity, in the sense that it should be thought of as the coordinate ring of the quotient space of your algebraic object by the action of the cyclic group. So it's the ring of invariance of the Weyl algebra under the action of the cyclic group, and you imagine that it's some kind of a non-commutative version of a Kleinian singularity. Okay, just because you're deforming, and this can be stretched a little further in the sense that, I mean, this invariant ring has a filtration by finite dimensional subspaces such that the associated graded ring is commutative, and is exactly what you would get doing through the Kleinian singularity process. Okay, so it's a non-commutative ring, but it has like the enveloping algebra of a Lie algebra. It's non-commutative, but it has a nice filtration by finite dimensional subspaces, relative to which the graded ring is just a symmetric algebra, a commutative algebra. Okay, here it's the same thing. These Smith algebras, or these quotients of the Smith algebra, are non-commutative, and I'm thinking of them as deformations of Kleinian singularities, and they are, to the extent that there's also finite filtration such that the associated graded ring is a commutative ring, and it's exactly the commutative ring that you would get as the coordinate ring of the Kleinian singularity. Okay, so this is kind of, I think, honest. So these will be honest, non-commutative deformations. Okay, so what story do I want to tell you? And I know I don't have a lot of time now. I think I've been abusing my time. So we know the representations, the finite dimensional irreducible representations of the Smith algebras by that classification. I should say that Smith actually in his paper already classified them. So we have the representations of a much wider class of algebras, these quantum generalized Heisenberg algebras. Smith already had the finite dimensional irreducible representations of the Smith algebras, okay? So our point was to study other irreducible representations. So for SL2, let's again get inspired by SL2. It's one of the few cases where all of the irreducible representations are classified. And this was done by Richard Bloch and later by Bavula with a different language. So the irreducible representations are either weight modules, and these are modules on which the Cartan subalgebra will act by eigenvalues. If you want, the action of the Cartan subalgebra is locally finite. So you take an element, you start acting by the Cartan, and you never leave a certain finite dimensional space, okay? And then there's some other kinds of modules called Whittaker modules, and then there are modules which are torsion-free over the Cartan subalgebra, okay? So this inspired us to look again also at modules which are torsion-free over the Cartan subalgebra in the Smith algebras. And we call them torsion-free, lack of imagination, torsion-free modules for the Smith algebras, okay? So these, you should think of them as complete opposites of weight modules, because on a weight module, the Cartan will act locally finite dimensionally, okay? An element, you start acting by the Cartan and you never leave a finite dimensional space. We're looking at the exact opposite kind of module, where the action is free. So there are no eigenvalues, and you're not living in a finite dimensional space. So it's just like you start take the element 1, for example, and start multiplying by polynomials in H. You will get, bigger and bigger things. Okay, there are no eigenvalues and so forth. Okay, so this is our point, and this is what I really wanted to tell you about. I wish I had an extra 10 minutes. But that's life. So hypothesis, F is an algebraically closed field of characteristic 0. It's more convenient to replace G. Remember, G is the commutator of Y and X. I want to replace G with a polynomial U that's such that the difference of U, the finite difference of U, is equal to G. So think of U as a finite integral of G. This is possible because we're in characteristic 0. There's only one convention that I want to, or one thing that I want you to remember. I'm going to correspond polynomials with their sets of roots, with their multi-sets of roots. Okay, so take a monic polynomial. The field is algebraically closed. I can look at the set of roots. It's a multi-set. There might be some multiplicities, and this is a bijection if I'm within, finite multi-sets, and if I'm within monic polynomials. So this is the correspondence. Okay, very, very simple correspondence. And I can tell you everything about these torsion-free modules in terms of this correspondence, okay? So by torsion-free, we mean, well, we're actually acting, the Cartan subalgebra will from the point of view of the Cartan subalgebra, the modules will be free of rank n. So the module looks like this, and H is just acting by multiplication. So that's the free action. And we need to see how the generators X and Y can act. Okay, so we have constructed simple representations of this form of arbitrary rank, but we haven't classified them completely. So the case where we have been able to, give a complete description of what everything looks like, and I think it's a very nice picture in terms of these combinatorics of the multiset, is the rank 1 case. Okay, so I'm going to focus on the rank 1 case. Okay, and what can I tell you? Well, first of all, is if I have a free action of rank 1, so a torsion-free module of rank 1, even if the module is not simple, it's still true that the center, the Casimir element, will act as a scalar. So it will still be a representation of these invariant rings, because the Casimir will act as a scalar, even if the representation is not simple. Okay. Now, we're going to show that these modules, even if they're not simple, they will always have finite length. They will have a unique simple socle, so they will have a unique simple submodule, which is torsion-free. And we're able to compute the composition factors. We were able to compute every composition series, the composition length, and the composition factors. And the composition factors will be in category O. So the composition factors will be 8 weight modules, except for the socle, which will be a free module. Okay, free for the Cartan. So it'll be simple. And so this is what I want to explain to you. So how are these modules constructed? It's completely combinatorial. So you fix a scalar that you like. This is going to be how the center, the Casimir element, is going to act. Then you take the roots of your polynomial u plus c, you look at the set of roots, and you form a partition of this multiset. Okay, with the block x of the partition, you form the polynomial q. And with the block y of the partition, you form the polynomial p, okay, with a certain shift. So it's not p of h, it's p of h plus 1. Okay, you shift it. So with these 3 ingredients, you define a certain module, which depends on c and depends on x. As a vector space, it's just polynomials in H. The element H acts just by multiplication. This is why this is a free module. And X and Y will act in the way that I'm showing here. So X takes a polynomial F, shifts it by 1, and multiplies it by Q. And Y takes a polynomial F, shifts it in the other direction by 1, and multiplies it by P. Okay, so what properties do these modules have? Well, the classification of the rank 1 free modules is given here in the slide. So they depend on C, they depend on X, and then they depend on a certain scalar lambda, which is a twisting of the action by lambda. Okay, so this is what the isomorphism classes of these torsion-free rank 1 modules are. They depend on 3 things: lambda, C, and X, and any module will be isomorphic to one of these for unique choices of lambda, C, and X. Okay, so this is a complete characterization. Okay. Second question, when are these modules simple? So I will forget about the twisting by lambda, because the twisting by lambda will give, everything will be the AC simple if and only if when I twist it by lambda, it's simple, and so forth. Everything is the same. Okay, so I'll forget about the twisting. So when is the module AC simple? And this is the interesting part. When more combinatorics start appearing, you look at the difference of the elements in X and the elements in Y. If that difference contains a positive integer, then your module will not be simple. If it does not contain a positive integer, then your module will be simple. So this motivates a natural definition, which is the following. I'll say that a scalar is less than or equal to another scalar if the difference of the two is a positive integer or 0. Okay, natural numbers, I'm including 0 in the natural numbers. So this is a partial order. Okay, with this partial order, I can describe, so we already know when the modules are simple. When the module is not simple, I want to find a maximal submodule. In fact, I want to find every possible maximal submodule. And then I want to iterate this process. So I'm going to give you the algorithm to do this. Okay, so you look at X and Y. If there is no positive integer in this difference, then your module is simple. You have your composition series, it's over, okay? If your module is not simple, then I'm going to show you a picture. But before I show you a picture, if your module is not simple, then there exists an element in X, let's call it beta, and there exists some other element in Y, let me call it beta hat, such that their difference is a positive integer, okay? So let me show you the picture. Here's the picture. So above I have X, and below I have Y. Since I'm looking at differences being an integer, I only care about the elements of X which differ by an integer, and the elements of Y which differ by an integer and which differ by an integer from the elements in X. Okay, so if you want my picture, I'm reduced to that. So the difference between any two elements in this picture will be an integer. Could be 0, could be positive, could be negative. Okay, so the fact that the module is not simple tells me that there is some beta in X and some beta hat in Y, such that their difference is a positive integer. Of all such pairs, I'm going to choose, so fixed beta. I'm going to choose an element in Y hat that is as close as possible to beta, in the sense that it's smaller. So the difference between beta and beta hat is at least 1, it's smaller, but it's as close as possible. And then I want to do the process in reverse. So look at this picture. I have, for example, this element here. The closest element in Y will be this element down here. So this is beta, this will be beta hat. But this is not good enough, because then if this were correct, then the closest element to this beta hat would also be this one, and it's not. The closest element to this beta hat is this one here. So in fact, I'm going to use this pair here, okay, beta hat. And the construction that I'm going to do, once I found a pair like this, which is as close as possible in this sense, I'm going to remove beta from X and put it into Y. And I'm going to remove beta hat from Y and put it into X. And I call this operation X star beta. It's a complete combinatorial construction. So you don't change the cardinality of X or Y, but you're switching a couple of elements. Okay. When you do that, you've constructed a maximal submodule. And in fact, every maximal submodule is constructed in this way. And so by this procedure, you will get a composition series for your module. Well, by repeatedly applying this process. So you will only get a composition series if this process ends. But I think from my description, it should be pretty clear that the process has to end. There'll be at some point where there's no more switches that you can do, and you've reached a simple module. Okay, so this is what you get. And the interesting thing is that you can do this in many ways, but the number of switches that you have to do is fixed. It's always equal to the number m. And the final set that you get, xm, the set where you've done all the switches and you can't do any more switch, this set does not depend on the order in which you've done things. And in fact, this submodule here is the unique simple submodule of your initial module. And it's still, as a vector space, isomorphic to polynomials in one variable. So it's a rank 1 simple module, and it's the unique submodule that this AC has. So if you want a comparison with weight modules in principle will have a unique maximal submodule, and you get a simple module by looking at the quotient. Here it's exactly the opposite. These torsion-free modules have a unique simple submodule, and well, that's the simple submodule that you get. So, well, one question is, I don't have time to ask you for possible questions at this point yet, so I'll ask the questions for you is, well, what are these successive quotients here in the middle? Okay, well, these quotients will be finite dimensional. Okay, so they will be finite dimensional simple modules. Okay, I'm calling them, they depend on a scalar beta, and I'm calling them L beta. What is the dimension of this L beta? Well, it's precisely that number K beta that I defined before, which was the difference between beta and beta hat. So that difference, that number, is the dimension of the simple module which you get in that process, okay? And conversely, any finite dimensional irreducible module for the Smith algebra will appear as the composition factor of one of these torsion-free modules, okay? So I think this is a very nice, kind of structure. And the final thing I want to tell you is that we can actually we can actually characterize all of the composition factors of these torsion-free modules and their multiplicities using very simple combinatorial functions, okay? So if I look at so first of all, I start with X, with the set X. I do this finite number of operations. I obtain the set X star, where I cannot do any more switches. And this will be the unique simple submodule that I have there. And it's of the same kind. It's a torsion-free module of rank 1. Then I look at a simple irreducible module, L beta, and I ask, what is the multiplicity of that simple module as a composition factor of my initial torsion-free module? And the answer is just this calculation on the post set. You look at the elements in Y, which are strictly below beta, and you look at the elements in X, which are weakly above beta. And you take the smallest of those numbers. That will be the composition multiplicity of your irreducible module L beta. And in particular, we have an exact formula for the length of the module, of our module, in terms of these very simple functions. So my question is, I mean, what are really, I mean, this is what it is, but I mean, are these functions appearing anywhere else? I mean, what could I find another interpretation for these functions, which maybe will give me some more insight about what we're doing here algebraically? I don't know. If you have answers, I'll be happy to hear them, but I want to stress, this is my last sentence before questions, which is, what have we done? So we started with a classical commutative thing with geometry. We're looking at these Kleinian singularities, these invariant rings, which are commutative rings. We've deformed everything, so we've switched the action of these finite groups from the polynomial ring into the Weil algebra. We looked at the fixed rings. And we realized that there were actually certain kinds of algebras called Smith algebras, or quotients of them. And we studied their representations. Okay, so this is, I mean, this is kind of a short version of what I tried to show you here. Okay, so thank you for your attention, and I'm sorry if I went over time.
Thank you very
Mikola,
much.
thank you for not having interrupted me, Mikola.
Oscar and Lucas, also thanks to you. Other questions?
Yeah, I have one question. Sam,
Hi.
so when you consider simple FH torsion-free modules over the Smith algebra, so are they of finite rank?
We have only considered finite rank. Yes.
Oh, I mean, if you have a simple module, torsion-free simple module, yeah, is it finite rank? Maybe not. I don't know.
I am not absolutely sure about that. I am not absolutely sure. We know a few things about the higher rank ones, which generalize some of the things that I've shown you. I am not sure if it's impossible to have an infinite. I would think that it's strange, but I wouldn't think it's possible to have a simple module that, yeah, I'd find it strange. I mean, my first attempt would be to prove that this is not possible, but
no, okay. Then you should have a example.
yes.
The other thing is, say you classified all simple modules over the Smith algebra of rank 1. So yeah, do you consider rank 2? I guess.
Well, we constructed simple modules of any finite rank, but we did not classify them. Okay,
Okay.
so we have some results in higher rank, which, well, I mean, I think we have proofs, but they're not, I mean, they're not in print. But I think I can say that we can prove using very different methods, so no longer with combinatorics, that they will still have finite length, which is kind of surprising to us in higher ranks. They will still have finite length, but for that we use completely different machinery. But we do not have a classification. And in general, I mean, these torsion-free, I should say that these torsion-free modules, for example, even for Lie algebras, they don't always exist. I think for Lie algebras, they exist in types A and C, and they don't exist in other types. And they're not in general classified. But we're certainly interested in trying going at it at a classification, but we haven't.
Yeah. So in your paper, you constructed simple modules of any rank. Yeah. That's nice. That is
we
nice.
did. Yeah. Thank you. Thank you.
Yeah. Thank you. Thank you. That's all my questions.
Thank you.
Thank you. And other questions? Other questions? Comments?
So did I leave everyone speechless? Hopefully not.
Well, you explained it very well.
Thank you. Thank you.
No questions.
Thank you.
Okay. If not, we thank Samuel once again.
Thank you all for your attention and for being patient. Thank you.
Yeah, bye, Sam.
Bye-bye.
Bye-bye. Have a nice week.
Thank you.
Yeah.